What's up? I'm with the next video from Haloalkanes and Haloarenes, and this time I'm talking about how haloalkanes are prepared. So this is going to be a little bit tricky, but along with that, it has reasoning, so it's also going to be interesting. For me, every time there is something reasoning, I feel like it's interesting. So the question is that how haloalkanes and haloarenes are prepared. I cannot discuss all of them together, but since I'm trying to make things in our sequence, so whatever is possible, I will do right now. What I have done right here is I have already written some equation, and because these are different and they can only be learned, but there's some reasoning coming out to be. So let's understand with that. If there is anywhere something specific, I will explain you that. So what we are talking right now. The one thing is the preparation of haloalkane is very common using alcohol. Why using alcohol? One thing you do know that alcohol is really easily available in a country like India, where this is I shouldn't change the topic right now, but you do understand what I'm trying to say. Alcohol is easily available in our country, and especially just because it's easily available, so alcohol can be used in many ways. And one of them is to prepare the haloalkanes. So how haloalkanes are prepared? The first equation here is, if you use any alcohol, this is about primary, secondary or tertiary, all types of alcohol. So if you use any alcohol and let it react with sodium bromide in presence of H2SO4, there is a displacement reaction. There R comes out to be with bromine, which form alkyl bromide. So in order to prepare alkyl bromide, you need to understand here. In order to prepare alkyl bromide, sulfuric acid is preferred because this makes the reaction faster. Basically the reagents are here, ROH and NADH, but this is used as a catalyst here in order to make the reaction faster. But there is one more reason also. What you see out here is there a byproduct here, water. This byproduct can be removed with the help of the sulfuric acid, because you do know sulfuric acid is a dehydrating agent. So this is the first method to prepare alkyl bromide. Okay, what next is, if alkyl or simply an alcohol is treated with phosphorus trihalide, it may be PCl3, it may be PBr3. Usually PCl3 is most used. So if alcohol is treated with PCl3, again there is a displacement reaction here, and it forms haloalkanes, and then other product is going to be like this OH react with the the halogen part and phosphorus part to form the phosphoric acid here, H3PO3. Now what third is, alcohol can also be treated with PCl5, because these are also easily available. And this case again the reaction is simply going through the substitution process. By the substitution R come out with chlorine and other some byproducts are. You have to remember that these are important products. Byproduct you can ignore for a moment. In some cases these are important. Okay, another method is that if alcohol is treated with red phosphorus. If you remember red phosphorus, what is red phosphorus? This is the second allotrope of phosphorus, which is not as reactive as the white one, but it's still abundant. So red phosphorus in presence of any halogen, when alcohol is treated, it gives the haloalkane. Other byproducts are also there, but that's I don't think is important, so I've ignored that. One last thing is, when alcohol is treated with SOCl2, which is the thionyl chloride. So there is something important, thionyl chloride. Thionyl chloride. So when alcohol is treated with thionyl chloride, the advantage is that most of the product here are in gaseous form. These two byproducts are in gaseous form. So if they are in gaseous form, what happens? These two evaporate into the air. So you get pure alkyl halide. So what you get? You get pure alkyl halide. I repeat back here. This reaction is very much important. Why? Because when alcohol is treated with thionyl chloride, what happens? You get pure alkyl halide. Why? Because other two byproducts are in gaseous form, so they evaporate, and you don't have to purify the RCl obtaining. So this is a method to prepare pure alkyl halide, right? Now what this next one is, when alcohol is treated with any hydrogen halide, you need to remember any hydrogen halide, but in presence of ZnCl2, this act as a catalyst here. So what happened? That R and HX undergo a mutual double displacement. You call it substitution. So it forms Rx. You form it Rx, and then it also forms water. Right? Okay. But there is something very important. There is reasoning also. This has to be, remember, if this is 1 degree or it's 2 degree. You need to remember, if it's 1 degree or 2 degree alcohol, only then this requirement is, very, very must. Otherwise, if it's 3 degree, let me write a 3 degree alcohol reaction here. R, take exact example, C, another C we have here, right? And this is with alcohol. So you do understand that this is a 3 degree alcohol. I hope you understand. So when a 3 degree alcohol react with HCl, it does not require ZnCl2. ZnCl2 not needed, right? This is not needed. You need to understand. And you get easily RCl, right? What kind of RCl is going to be? Well, simply you have to remove OH and place chlorine back there. So you get this kind of, this kind of haloalkane. And along with that, you also get water molecule as a byproduct. So you need to understand that if the alcohol is 1 degree or 2 degree, a catalyst is required. But if it's 3 degree, no catalyst is required. Now the question is, why in case of 3 degree, there is no need to have a catalyst, and why in case of 1 degree or 2 degree, there is zinc chloride required? Because this produces tertiary carbocation. You need to understand that the carbon is 3 degree. So if this bond undergo cleavage, I'll tell you in some other equation, because organic chemistry is something else coming up. So if this bond breaks, this form a carbocation. However, this carbocation will be a 3 degree, and a 3 degree carbocation is most stable. And if the carbocation is most stable, definitely the substitution is quite easier. This is like somebody who is most stable in the society gets friends quite easily, gets married quite easily, because people are looking for stability in life, and that is what happens. So because 3 degree is more stable than 1 or 2 degree, so substitution in this case here is quite easy, and no need of zinc chloride is, so there is no need to have zinc chloride. But in this case, you need to have zinc chloride, because there the 1 degree and 2 degree alcohols are not as reactive and not as stable as the 3 degree. I hope you understand. Now, what next I'm talking is something coming out to be from the 11th also. In 11th, you have studied how haloalkanes are prepared by free radical mechanism. So the second process I'm talking is free radical reaction. Free radical reaction. Though this requires a mechanism, but I can't take every time a mechanism. So when it's the way it has to be done here, I will be doing. So what free radical mechanism is? What happens when a methane, when an alkane, let's write it in common way. When an alkane react with X2 in presence of light, it produces alkyl chloride. This become alkyl halide, sorry, because I have X here, alkyl halide. And along with that, you also have, HCl. Okay, let's take the example. Suppose I am talking about, this particular alkane. Let's take any alkane we can consider. So this is a butane. When butane react with halogen, you need to understand that this reaction takes place in presence of light. So what happens? This undergo cleavage. Now this is something from 11th class. I'm really sorry right now, because if you don't get it how this bond undergo cleavage, really going to be a little bit tough. But you need to go back and check out how free radicals are formed, how they react. In case you don't, I will try to make it in some other video, because you do know that all these I have started is not some old activity. I've started this past month, so I cannot provide all the videos together within very short period of time. So I'm really sorry about, in case you don't know what free radicals are and how they are formed. But right now I'm considering that you understand. So what happened? There are 2 degree carbon here, and there are 1 degree carbon here. This is also 2 degree, and this is also 1 degree. So what happened in this case? 2 types of product will be formed. You will have halogen here, but you will also have halogen over here. So this is going to be the minor product, and this is going to be the major product. Why it's major? Because it's symmetrical and therefore it is more stable. This is a bit unsymmetrical, so it is less stable. Right? Mechanism I'm not taking, but I hope this will help you. So this is what called, free radical reaction. Let's take another example from the same. If methane react with chlorine, but that has to be in presence of light. So what happened? This initially form CH3Cl plus HCl. But if the reaction continue, this will produce dichloromethane. So this will be CH2Cl2 plus HCl. So let's write the last one. So if it's like CH4, if I write CH4 plus Cl2, in presence of light, ultimately what will happen? All the hydrogen will be replaced and this will become carbon tetrachloride plus 4 HCl will be produced. In order to balance, you can do your balancing like 4 and 4, 8. So this is going to be 4 here. Right? So this is how free radical mechanism takes place. In case you need further more example, do let me know. But this reaction is completed in presence of light and it follow free radical reaction. In case I need to repeat what free radical is, I am repeating in very short. When a covalent bond breaks in such a way that the shared pair of electron is distributed to each of the participating atom, then the bond cleavage is called homolytic. But if the bond breaks in such a way that the shared pair electron goes with one of the atom, it is called heterolytic cleavage. So this start with free radical. You need to remember, every time a reaction takes place in presence of light, this follow free radical reaction, especially reaction from the organic chemistry. Right? Electrophilic substitution reaction. Okay, so the reactant here is being taken like methyl benzene. So this is what the reactant is, and what you have to do, you have to react with the halogen X2. Right? Now, what happened here? There is something very important. In this reaction, there are hydrogen on benzene also. There are hydrogen also. There are two types of hydrogen. One is on the alkyl group, other is on the benzene. Two types of product. One you have already here, CH3. So this form, there. But also another product. And that's going to be X here. So what happened, in case you want to get through, this is an ortho position. So what happened, and this is a para position. This is your ortho and this is your para position. This is 1, this is 2 and this is 4. So because alkyl group, you have to understand that alkyl group is a plus R effect. It gives plus R effect, and because it gives plus R effect, what has to be done? The substitution takes place either at the ortho position or at the para position. So that's why halogen will be shifted to either second position or fourth position. But there is one more thing here. There will be a byproduct which is also going to be HCl. Now this is going to be a minor product here. You need to understand this is going to be minor. This is going to be major. This is going to be major. Another thing is that this has a higher boiling point, and this one has a lower boiling point. So separation of these two compounds involves distillation, because distillation can easily separate these two chemicals because they have a wide gap between their boiling point. So if you heat the mixture of these two compounds, this will evaporate faster and can be condensed to separate out, while this will evaporate later on because of having the higher boiling point. So that's how they are separated. This reaction is called electrophilic substitution reaction, and the reason is that one electrophile, you need to understand. Another thing I missed here, that an electrophilic substitution reaction always takes place in presence of a Lewis acid. I'm taking an example here. Lewis acid like AlCl3. There is also a deep and quite long mechanism here, but I'm not taking them right now. Electrophilic substitution reaction में बेसिकली क्या करना है आपको ये करना है कि चूंकि ये जो है ये प्लस साइड इफेक्ट देता है, तो आप क्या करोगे, या तो सेकंड पोजीशन पे हाइड्रोजन को हटाओगे, उसकी जगह हेलोजन लगाना, या फोर्थ पोजीशन के हाइड्रोजन को हटाकर उसकी जगह हेलोजन लगाना। तो जब वो सेकंड पे लगेगा तो दिस विल बी sorry for one more thing, that measure is going to be right there. This is going to be the measure here. So अगर वो if the halogen is on the fourth position, it's going to be major. If the halogen is on the second position, it's going to be minor. The minor one has a lower boiling point. Major has a higher boiling point because it is symmetrical. This is unsymmetrical. So they are separated by distillation process. So I hope this will help you. But though I'm a little bit not sure because of some other topic related to that. In case you are not sure ki how the what Lewis acid is, how the mechanism start. So what you can do at least is you can remember that when toluene or any alkyl benzene react with halogen either go on the second position or go on the fourth position. The compound with the fourth position halogen is a major one. Why it's major? Because it is symmetrical, and the other will be a minor product, so it is unsymmetrical, and they are separated by simple distillation process. So I want to wind this video right now here, wind this up, and we'll tell you in coming video about the rest of the topic. So that's it. Thanks for watching.